this assessment asks us to complete table 5.1 with 5 different values. You can already tell there's a lot on the screen. This is going to be a complicated video, but let's wing it together. I've gone ahead and put the equations that are going to matter. Delta G equals negative RT natural log of KEQ. Rearrange that. KEQ equals E to the negative delta G over RT. The temperature was given as 25 degrees plus 273 gives 298 Kelvin, so we'll use that. If we want to calculate a ratio of a percent B, we'll take B over B plus A times 100. And the value for R, we're going to use 1.987 is in calories. That's going to matter here in a minute. All of this is for the reaction A going to B. I've got notes that I'm going to look at. I don't have these calculations in my head, but let's get started. All right, the first, we're given a delta G of plus 0.5 kilocalories per mole and asked to calculate KEQ. That's that reaction going from A to B. It's going to be slightly uphill, so we're going to expect a KEQ to be slightly lower than 1. If we plug those into the equation, so I'll try to write somewhat small so we can fit all of this in the space we have. The equation we're going to use, KEQ, is going to equal E to the negative 500 over 1.987 times 298. So E to this whole quantity. Now, why did I use negative 500? Because R is in calories, so we've taken this 0.5 kilocalories and gone ahead and converted it to 500 calories. When we do this, we calculate a KEQ that is 0.429. So the value that we would put for number 1 is 0.429. And that KEQ is slightly less than 1, just as we expected, based on a slightly uphill reaction going from A to B. Part 2 asks us to take that KEQ and calculate the percentage B. Now, when we have a KEQ of 0.429, what we really have is a ratio of B to A. Remember, KEQ is the products over reactants. B is the product, A is the reactant. So our ratio of B to A is actually 0.429 to 1. Right? If we calculate a KEQ of 0.429, that means we have a ratio of 0.429 of B to 1 of A. And so we can calculate the percentage B by taking that 0.429, the amount of B we have, over the amount of everything in solution, 0.429, that's the portion that's B, plus 1, the portion that is A. Multiply that times 100 to convert it into a percentage, and we're running out of space, but we get a value that is 30%. So we have 30% B. That is the answer to part 2. Moving on to part 3, we're kind of jumping ahead. We're given a KEQ of 5.4. That means the reaction is favored to the right. We're going to expect to have a percentage of B that is greater than 50. Remember, at KEQ equals 1, that's when you would have a 50-50 mixture. Since KEQ is greater than 1, we should expect to have more B. We'll use the same concept that we used in the earlier question, where the ratio of B to A is essentially that KEQ. So 5.4 over 1. Solve for percent B in the same way. 5.4 over 5.4 plus 1. That's B over A plus B. Multiply that times 100, and we end up with 84%. So just as we expected to have greater than 50% B, we have 84% B. And if you notice as you go through, if you compare these values to the ones that are given in the table, they fit, right? They fit where we would expect them to be. KEQ greater than 1 gives us a greater than 50% of B, whereas our KEQ of less than 1 gave us less than 50% B, just what we expected. Let's jump ahead to V because we're using calories and kilocalories in this, or 5. KEQ here is 859. We're going to calculate delta G. For that, we're going to use this equation here, put 859 in for the KEQ times negative RT, and that will give us that. So let me do that down here. This is the first time I've ever gotten on my knees for one of these videos. So delta G is going to be equal to negative 1.987, that's negative R, times 298, that's the temperature, times the natural log of the KEQ, which is 859. Plug those values into your calculator, and you end up with a delta G equal to negative 4 kilocalories per mole. Now, if you had looked at the table and estimated, you might have predicted that number because the one right above was negative 3.0, the one right below was negative 5.0, and this seemed to fit right in the middle based on that other data. So the answer to part 5 is negative 4 kilocalories per mole. We can now answer part 4 a little bit more easily using this value in kilocalories. Recall that to convert kilocalories to kilojoules, we're going to multiply by 4.18. So if we take negative 4 times 4.18, that's the conversion factor for kilocalories to joules, we end up with negative 16.7 kilojoules per mole. And that's the answer for part B. And I just went off the screen. If this were a high-tech production, I would re-record, but I'm not doing that. Hopefully all this makes sense. If you need to rewatch it again to kind of go through it more slowly, please do. But that's it.